All right, hello and welcome to the fifth lecture of Chem 390, where this one, I'm sure you'll be glad to hear, will be a little bit shorter than the previous lectures for two reasons. The first being that the first three lectures of the course were much longer than I intended. I intended each lecture to only run about an hour or so, and some of them were like an hour and a half. So this is to sort of make up for that lost time and try to give you back some time as you work through this course on top of your other, I'm sure, busy schedule and commitments. Before we get into the content of today's lecture, let's quickly recap what we discovered. We didn't discover anything, we learned. Other people discovered this. And what we covered was the impacts of wildfires on water and soil. So really, I really should reverse these two to better reflect the chronological events that occur after a wildfire, because it's really the impacts on soil that trickle down and impact the water. Where we learned that in soil, what happens is we can have this tin roof effect that we talked about, where basically if we have a soil layer here, and let's say like the bedrock is down here, what happens in a wildfire, or rather after a wildfire, is that a hydrophobic layer, so hydrophobic, remember this is just chemicals that don't like to mix with water, so we form a hydrophobic layer parallel to the ground, to the soil above this layer. And what happens then is when it rains, water, let's get a lighter blue for water so it's clearer. Water, when it rains, seeps into the ground, hits this hydrophobic layer, and since it doesn't like to mix with it, rather than seeping into the bedrock and going into groundwater like it usually would, what instead happens is it skirts off the surface of this hydrophobic layer and it can carry a lot of the soil with it. So this causes a lot of soil erosion. Okay? And I'm not really depicting it in this drawing here, but usually natural waterways and watersheds will be oriented such that water will flow downhill. So let's suppose this soil is on a hill. So normally water would strike the hill, seep into the soil, into the groundwater, make its way into a stream somewhere or some other natural waterway. With this hydrophobic layer, what results is this tin roof effect, where the hydrophobic layer acts as a tin roof, water hits the tin roof, skirts down the surface of the tin roof, and carries a lot of the stuff with it that's on top of the tin roof, okay? So hopefully that analogy is making sense. And additionally, so this was step one of how wildfires increase the concentration of contaminants in water. Step two was that simply by heating up soil, so simply by the fact that fire is hot and heats up the soil underneath it, it chemically changes the soil so that it is more, so that the organic components in the soil are more water extractable, okay? So what we saw in the last lecture was that carbon and nitrogen become more soluble in water as a result of simply the soil being heated up. So more soluble in water. So the increased soil erosion increases the amount of sediment that gets washed into natural waterways and streams and such. And then this heating effect causes the organic matter in that soil to leach out of the soil and enter the water, where this sort of impacts water treatment processes that occur to treat the stream water or the groundwater or etc. And particularly what it does is this increased organic matter content. So this increased organic carbon and nitrogen. So remember, when I say organic carbon and nitrogen, I'm referring to a wide variety of molecules. There's not one molecule that makes up organic matter. There's several. But it's usually some combination of carbon, hydrogen, oxygen, and because we're talking about organic nitrogen, some of these will also have nitrogen there. I'll give it a subscript, I don't know, N. Okay? But basically, there are increased amounts of these organic compounds in water. So in a water treatment facility, what happens is the coagulation process of causing things to clump together, that process becomes much less efficient, which increases the amount of organic carbon and organic nitrogen species present in this disinfection step, where remember, disinfection is where you mix some oxidizing chemical, whether it be chlorine, bleach, ozone, UV light could be used. UV light wouldn't cause these disinfection byproducts to form, but let's just say we were using chlorine. What happens when there's a lot of residual organic carbons and organic nitrogens present is you form a lot of trihalomethanes. So in this example, that would be something like chloroform. And you can also form a lot of haloacetonitriles, which have the general chemical formula of C2H2, right? Yeah, H2NCl. Okay, so both of these things are harmful to ingest. Not to worry, any good water treatment facility monitors these things very thoroughly. Trihalomethanes, haloacetonitriles, all sorts of these disinfection byproducts are constantly monitored. And what a water treatment facility would do is not simply just give you this horrible water to drink, but rather they would continue treating it until it's safe to drink. And in doing so, this extra treatment required to get rid of these trihalomethanes, these haloacetonitriles, which results in more cost, more coagulant chemicals needed, more disinfection needed, a second coagulation step post-disinfection to get rid of these trihalomethanes, haloacetonitriles, and introduces a large cost, which for rural communities, which don't have a significant amount of funding, let's say, for these sorts of endeavors, in some cases results in the water treatment facility shutting down. So it has a very dramatic impact in some cases, okay? So then today what we're going to talk about is, okay, I told you burning plants introduces organic carbons, organic nitrogens into the water through these mechanisms of soil and water chemistry that we talked about here. But now a question you might have is like, okay, plants can be a lot of things. There's a lot of different kinds of plants, okay? So how do those different plants impact water and soil differently, okay? So for today, we're going to be diving into that topic. I guess we're not really going to be diving into it. We're going to be looking at it at a very surface level just because there is so much complexity in this region of wildfire chemistry. And we just simply don't have the time in this course to really delve through each of the different chemical changes that results and what their impacts are. So we're just going to focus on organic carbons, organic nitrogens for the most part. And we're going to look at just 5 different tree species where in the US and really across the world, there's a myriad of different plant types. And for today, I'm just going to be focusing on 5 different trees. So aspen trees, pine trees, oak trees, spruce trees, juniper trees, all of which exist in especially the Pacific Northwest and the mountain region of the United States, so meaning like Colorado, Utah, Wyoming. These trees are sort of familiar to or native to all of those regions, okay? So the motivating questions that we're going to be digging into today is first, How do these different trees impact soil and water chemistry? So are there any major differences? And if so, are any of these types of trees particularly harmful or less harmful? Which is certainly something of interest to um, like surrounding communities in a wildfire. So if you're surrounding an area with a lot of aspen, should you be particularly worried about water quality post wildfire compared to if you're in an area with a lot of oak trees nearby? And then also, could these results or this research of differences in how different plant matter burns, could this be used to our advantage? Meaning, if let's say a certain type of tree is less harmful to soil and water, could those types of trees be planted in reseeding efforts, which are already done post wildfire? Could we particularly say, hey, let's plant more pine trees this year round because we know it will impact water less harmfully? And these sorts of questions of reseeding efforts certainly are limited to what is ecologically sound. So obviously, if an aspen isn't native in a certain area, well, it probably wouldn't be a candidate for a reseeding effort just because you don't want to disrupt natural ecosystems and natural ecology that exists. But within the realm of within reason, these sorts of questions are very interesting to ask, where how can we better remediate the effects of wildfires, and reseeding is one way to do so, okay? All right, and like I said, there is a lot of chemical complexity here, so there's a lot of data on this slide. And I even say here, there's a lot of chemical details that can be measured for each of these different types of trees. So in this one study here, what the researchers looked at were all of the trees I listed plus firs. I didn't find other studies that also looked at firs, which is why I excluded them from our lecture today. And you can see what they measured was the various metal content and various elements that were measured in the ash and also the soil of the underlying soil from when these trees burned. And this is milligrams of element per kilogram of ash or per kilogram of soil. Okay, so that means researchers took a kilogram of soil, they measured how much calcium was in it. They found that, hey, look, there's 159,735 milligrams of calcium in this kilogram of soil. Okay, so these are all, you should think of these numbers here in a relative sense. And also, I guess I should mention, you're not going to be responsible for knowing all of these slight differences and how much vanadium is produced from a pine burning versus an aspen burning. Those are certainly interesting questions and interesting data to know, but maybe not so much for our course, okay? So, as I say down here, we're going to focus, again, just like our last lecture, mostly on organic carbon and various forms of nitrogen, okay? If you are very interested in these things, I will briefly break them down into categories that you can research later on your own. So for instance, calcium and magnesium content. The amount of calcium and magnesium is referred to as hardness. So water hardness is how much calcium and magnesium are in there. These can cause a lot of deposits where they like to form insoluble calcium carbonates and magnesium carbonates. So these are insoluble in water, and they can form deposits in pipes and in plumbing systems and cause changes in flow rates and stuff. So it's generally a good thing to control these, not so much from a health perspective, like it's good if you ingest calcium and magnesium in obviously certain doses. So really what these are harmful for in water and why people care about these things is because of forming deposits and stuff. So if you ever notice when water dries, it leaves like a little white circle where that droplet once was, that's going to be calcium and magnesium carbonates that are left behind from the hardness and the water. And there's certainly a whole slew of other metals in here. A big one here is lead. So lead, very bad because it's toxic, passes the blood-brain barrier, can cause a lot of neurodegenerative issues, especially in children who are exposed to lots of lead. So this is obviously another big one that would be of concern to remove from water and soil. And there's also a bunch of other metals here that are somewhat relevant to the plant life. So a lot of proteins use metals like iron and manganese and copper and nickel, and even zinc is used with some DNA processes. So these are all sort of natural to plant biology and just living organism biology in general. Yeah, I think I'll stop there with giving a brief overview of this stuff, just because it can get a lot more. We just don't need to venture into that territory, okay? So like I said, we're going to focus on organic carbon. This is often measured in water as dissolved organic carbon. So dissolved organic carbon, which we've seen before, I believe. And then we'll look at various forms of nitrogen. So we talked about organic nitrogen in the last lecture. What we're going to talk about today, well, I guess we didn't talk about just organic nitrogen. We just talked about nitrogen in general, of which organic carbon is a subset in just dissolved nitrogen. But today what we're going to be focusing on is nitrite, which we will cover in our toxicology why did I say lecture, and nitrate, which will also be covered in our toxicology lever. I said lever again, lecture. Okay, so yeah, how do these things differ based on these different trees burning, okay? So a good question to ask is, why do plants produce different amounts of chemicals when burned at all? Okay, so a lot of this has to do with combustion efficiency. Where certain plants just naturally are composed of, or rather their sort of physical composition lends itself to burning hotter and therefore more completely. So I guess I'll just put that in writing here. Okay, and we could sort of see some of what I'm referring to as physical traits. You can see some of those on the images I had on this slide here, where I'll let you sort of form your own hypotheses here, but something, I guess I'll just pick one out in particular. So let's say like a juniper plant tends to have fairly thin branches, thinner, less stocky trunks, is more composed of dispersed plant matter that is easily ignited. Like it's more fuzzy, I guess you can say, in non-scientific terms. Whereas something like an oak or an aspen has significantly less leaf foliage, at least relative to junipers or like spruces or something. And as a result, a lot of the plant mass, like let's say for an oak tree, which has a really, really thick trunk, a lot of the plant mass is on the interior of the trunk. So as a result, maybe it would burn a little bit less hot, a little bit less completely, and thus resulting in slightly different chemical changes. So like I said, take a look at some of these pictures or look up some of your own pictures or use your own background knowledge on trees and plant ecology and see if you can have a hypothesis where some of these plants might burn more completely, some less completely, okay? Where really what this results in, remember, is less complete combustion results in more organic carbon. So remember, when I'm referring to combustion, I'm referring to this chemical reaction of plant matter, which is a lot of polysaccharides for the most part, so lots of glucose molecules linked together, reacting with oxygen to form carbon dioxide. So less complete combustion means that there is less of this process going on, less CO2 formation, more so forming these organic carbons, elemental carbons along the way to forming that CO2, okay? So this is one big reason why plants would produce a different chemical output, let's say, and their ash and what ends up resulting in water and soil as a result of these plants burning. And then another big one is just simply inherent differences in their chemistry. So we talked about this a little bit already, where tropical plants, let's say, so an example that we already saw was tropical plants versus like temperate or boreal plants, or plants in those regions. Where tropical plants tend to have more nitrogen, these tend to have less nitrogen. Things like this, things that are just inherent to the biology and the biochemical processes of these plants will lead to slightly differences in the chemical output from when they are burned. So something like an oak tree might have a little bit more polysaccharide content in the form of like lignin for those really thick, stocky trunks, whereas something like a juniper might have more nitrogen content for the higher amount of I don't know, leaf matter or something that might be more nitrogen intensive, something like that, okay? So yeah, these are the two sort of main differences here. So let's take a look here at a breakdown of these different types of trees and then their relative carbon and nitrogen content that is produced, okay? So when I say carbon and nitrogen content, what I'm really referring to here is a mixture of what is present in the ash after the fire, what is present in soil, and what leaches into water should the soil and ash be exposed to water. So I'm sort of combining all of those into just how much carbon total is present generally in the ash, the soil, and water for these different types of trees, and then also how much nitrogen. Particularly, there was a lot more data in the form of nitrites and nitrates, so I picked that specifically. So how much nitrates are present in the soil, the ash, and in water after these types of trees burn, okay? And what we see in the nitrogen content is maybe a little bit expected based off of our tropospheric ozone chemistry lecture, where, you know, a lot of these trees, all of these trees are native to boreal and temperate regions, and as a result are going to have, like we talked about in our tropospheric ozone lecture, lower nitrogen content that is produced in the soil and ash afterwards, okay? And then, interestingly here, the relative amounts of organic carbon in the ash sample tends to be a little bit more variable, and this is for reasons that most researchers suggest is due to combustion efficiency, so just the physical traits of the different plant matter that is displayed for these 5 different trees. So something like a pine will have sort of a medium amount of carbon that ends up in ash and soil. So like I said, this is technically ash / soil / water. I guess I didn't update this slide for that. Sorry about that. So it's a combination of the 3. And something that's interesting to highlight here is the oak tree. So the oak tree had relatively high levels of organic carbon present and nitrogen present afterwards, okay? So the oak tree will likely, or is expected when oak trees burn, that there will be more organic carbon more nitrogen in soil and ultimately in water. And what's interesting about this is that the oak tree could be considered good or bad, that it has these high amounts of organic nitrogens, organic carbons in soil and in water post-wildfire. Because we talked about in our last lecture that this leads to negative impacts to water treatment chemistry. We'll just say water treatment. Remember, the big end result here is more cost required to treat water. But an interesting alternative view of this is that this could possibly be beneficial for reseeding efforts. Which we touched on this before, but basically the idea here is that reseeding is the introduction of seeds into soil post-wildfire, with the idea being that more plant matter will grow in the more quickly in the following months, and that helps to decrease soil erosion if there are plants above the soil to absorb some of the water and prevent just large sediment runoff post-wildfire. So that's sort of the main goal of reseeding efforts, where because and the reason why oak trees are particularly interesting for these reseeding efforts, the reason is because the higher amounts of organic carbon and nitrogen in soil are beneficial for new plants to grow. Where plants obviously need carbon and they need nitrogen in order to grow. That's why, we have fertilizers. Fertilizers is a source of nitrogen and nutrients for plants to grow. So the idea here is post-wildfire, what if we were to plant more oak trees in addition to, other plants to maintain, a naturally healthy and diverse ecosystem. And the logic behind this is that during a, let's say, prescribed fire, or should a wildfire return to this area, the plant matter that would be burning would be partially oaks, because that's what was planted in reseeding efforts, and sort of enhancing this cycle of benefiting future reseeding efforts, where the presence of the oaks will allow more plant matter to return in a quicker time scale post wildfire. So it was just an interesting conservation point that I saw expressed in some research articles, where researchers did actually see differences in reseeding in areas that had wildfires where it was predominantly oak trees versus, in that particular study, it was juniper trees is what they compared them against. And they noticed that reseeding efforts, I believe it was 6 months after the fire in the region with the oak trees, there was already like regrowth occurring, like they could see new plants budding out of the soil, whereas in the juniper area there was nothing whatsoever. So just an interesting idea here, okay? And that this goes both ways. You could argue something like spruce and juniper are the most beneficial because these produce the lower amounts of organic nitrogen and carbon. So these produce lower amounts of organic carbon and nitrogen, which, if we think downstream to what this organic carbon, this organic nitrogen, some of it eventually will end up in natural waterways. So this could pose smaller negative impacts to the water treatment industry and water treatment facilities. And I'll put a question mark there for both of these, because this isn't really well-documented, well-studied stuff. It's just interesting ideas that are being discussed at least in the world of wildfire chemistry being sort of discussed there. And another interesting angle to look at this is this was analyzed in ash, soil, and water, so perhaps by association you could assume the smoke produced from these different trees. So could this be reflective of smoke? So could these results be reflective of smoke? If so, that would have interesting implications on the environment that we've already talked about. So what I mean by this is, if a spruce tree or a juniper tree produce low amounts of nitrogen and carbon, at least in their ash and their soil, the same might be true of the smoke and particulate matter that they give off when burned. And remember, nitrates, so NOx, is what led to ozone formation in the troposphere. So if there's less nitrogen content in the smoke, that's a lower amount of ozone that forms in the surrounding area. And then remember, organic carbon destroys ozone, so I'll do an arrow with an X through it. So this is in troposphere, and then this ozone that is in the stratosphere. So perhaps the potential benefits of oak trees with reseeding efforts do not offset the possibility of more NOx emissions that would lead to tropospheric ozone, or more organic carbon emissions, which lead to the depletion of ozone in the stratosphere. So these are just really interesting questions, I think, when analyzing this sort of stuff. So if the goal, or rather the end result of this, is that oak trees or oak plants are used more for reseeding efforts, there should be a lot more research done, and how do the atmospheric effects of these different trees burning change, and yeah, so I guess that's mostly what I wanted to talk about in this lecture. Hopefully it was somewhat interesting. It was a lot of very speculative science, so yeah, I guess just take these results here with a grain of salt, and yeah, so I guess looking forward in the course, where we're moving now towards here is that we've talked about, like thus far in the class, we've talked about a lot of things that can form in wildfire smoke. So we talked about, so this was in smoke. We talked about elemental carbon, organic carbon. We talked about ozone in the troposphere that we could be exposed to. We talked about water chemistry, so we talked about more organic carbon, but particularly we talked about disinfection byproducts. We talked about, so that was trihalomethanes and haloacetic nitriles. We talked about just organic carbon in general. Well, I guess we're going to assume that the organic carbon gets treated in okay, well, we'll leave it in there. We can talk about toxicology. But where I'm going with all of this is we talked about a lot of things that occur in the air and water. So then now the guiding question for our next lecture is, what happens when living organisms are exposed to these? We talked about what happens when the atmosphere is exposed to these. There was a lot of negative effects to ozone in the stratosphere and ozone in the troposphere. There was negative effects to, like water treatment municipalities, that sort of stuff. So now we're going to turn to what happens when living organisms are exposed to these and ingest them. Okay, so stay tuned for that lecture. Good luck with exam 1. And that's pretty much all I had for this one. So hopefully you'll enjoy a nice shorter lecture load this week. And I will see you in the next lecture video.